7.4, evaluate logarithms and graph logarithmic functions. Logarithms are the inverse of exponential functions. We'll talk about more about what that means shortly. The important thing you have to be able to do is translate between what's called logarithmic form, which we see on the left here. Bad color. And exponential form. This is basically a formula that you have to have memorized. Anytime we see something like 2 to the third equals 8, which is true, we can rewrite that in log form. We keep the base the same. The base on the exponential was 2, so we keep the base 2. That exponent is now on the other side of the equal sign, and the 8 goes here. These both say the same thing. They're both true statements. One easy way to help remember how to read this log statement is start with your base, 2 to the third power equals 8. 2 to the third equals 8. Notice that's the same thing I have written over here. So our first example is really just going to be practicing writing all these out. Over here in part A, we see log base 2 of 8 equals 3. So to rewrite that as exponent, we go 2 to the third equals 8. Just like we see there. 4 to the 0 equals 1. 12 to the 1 equals 12. And 1/4 to the negative 1 equals 4. That one's kind of the hardest one. Remember what we do about a negative exponent. To make that a positive exponent, what do we do to the fraction? That's right, we flip it. And 4 over 1 is the same as 4. The first power is 4. So 1/4 to the negative 1 power is 4. Right now, go ahead and pause the video and rewrite all 4 of these logs as exponents. Our next example, we're going to evaluate logs. We want to figure out what log base 4 of 64 is actually equal to. And the way we do that is first we say it equals something. We'll call that x. Now we get to rewrite that in exponent form. So we might say something like 4 to the x equals 64. And we should be able to solve that in our heads. 4 to what power equals 64? X equals 3. Following the same kind of idea, I'll come back to part B. I think that one's actually the hardest one. Part C. Once again, we say something equals x. 1 over 5 to some power equals 125. That's kind of tough because you look at that 1/5 and think to yourself, I don't like that fraction. But just like our exponential section, we're going to get rid of that fraction by flipping it. But if we flip the fraction, what do we have to do to the exponent? Make it negative. Oops. This still might seem kind of hard to solve, but you should be able to, in your head, decide 5 to what power equals 125. 5 to the first power is 5. That's not going to help us. 5 to the second power, 25. 5 to the third power, on the other hand, is 125. So in your mind, we're thinking 5 to the third equals 125. So what does x have to be? X can't be 3, but x could be negative 3. Because negative of a negative is a positive. Let's look at part D. 36 to what power equals 6? Again, this is kind of hard. I I see 36 and 6, they're not really the same number, but 36 can be rewritten using a 6. And our exponent for 6 is just 1. We can go a little further with that, multiply the exponent, 6 to the 2x equals 6 to the 1. Since our bases are the same, our exponents must also be the same. So x equals 1/2. We could have actually done something like that for part C also. A little side quest over here. 125 we know is 5 to the third, so we could have written 5 to the negative x equals 5 to the third. The bases are the same now, so the exponents are the same. Negative x equals 3, x equals negative 3. Last one of these we're going to look at. I'm going to put it on a different page so I'll have room. Start them off the same way we started the other ones. 5 to the x equals 0.2. The reason I think this one's hard is because of the decimal. We should really write 0.2 as a fraction instead of a decimal. Hopefully we'll see something that has a 5 in it. So side quest, 0.2 over 1. If we want to rewrite that as a fraction, we need to move the decimal over one place. And we get 2 over 10, which reduces to 1 over 5. So this is really 5 to the x equals 1 over 5. We could say to the first power. These bases don't quite match. One's 5, one's 1/5. We can make them match by flipping the fraction over and changing the sign of the exponent. Now the bases match, so we can say x equals negative 1. Done. Next up, we are going to practice typing into your calculator logs and natural log. Notice both of these don't have a base. When we see log of 8, that really means log base 10 of 8. When you don't put a base on a log, it automatically means your base is 10. Go ahead and type that in your calculator and verify that you get this result. And the way you can check that is by writing it as an exponent. That ln that you see, it also doesn't have a base. ln is really pronounced natural log. And the base that's always there is e. You remember from the previous lesson that e is just a number, approximately 2.7. Find that button on your calculator, it's an ln. Do ln of 0.3, plug that in, and check your answer. That's it. At this point, go ahead and pause the video. Try all 4 of these on your own. You're just typing into a calculator. The ones, I take it back. Some of these are plugging in the calculator. The first couple you are doing by hand. Directions say use a calculator if necessary. We don't even know how to use a calculator unless the base is 10 or e. Most calculators don't have any other base than that. We will learn a way to deal with it, but not yet. Moving on. A couple of formulas that you kind of have to remember. 2 formulas we have to know. This guy and this guy. All it's basically saying is that if the base and this number match up, you can simplify it to just being x, or whatever your exponent is. Similarly, if you have a bases match up here, that also simplifies to x. So looking at these examples, remember, since there's no base there, the base is really 10. The bases match up, so this is 4. Over here on this next one, the bases don't match up. It's 5 and 25. Those bases don't match up. Instead, we have to rewrite this a little bit. We know if 25 is the same thing as 5 squared. Multiply the exponents. Now the bases match up. So this whole thing simplifies to 2x. Done. It's really just a way to take something complicated and make it look a lot simpler. Next up, we're going to find inverses. This idea should sound totally familiar. If you're thinking the first step to finding an inverse is to switch x and y, you are absolutely right. So that's what we're going to do. Now we have to get y by itself. So we're using the property that we learned at the very beginning. And if we have some exponential function, we can rewrite that as a log function, like so. So if I'm going to write this as a log, I keep my base the same. In this case, it's 6. My exponent moves to the outside, other side of the equal sign. Which leaves my x to go right there. That's the process. I think it's harder to go this direction than the other direction. I think it's a lot easier if you start with this and go back to there. But you have to be able to go both directions. Part B, once again, we start by rewriting, by switching the x and the y's. I don't have a base, but since it's a natural log, I'm supposed to know what the base is. I need to know that the base is e. Now I can use that property that we've seen ever since the first slide, e to the x equals y plus 3. Y is not by itself yet, there's one more step. We've got to subtract 3 from both sides. Now we're done. And by the way, we should know how to graph this. We should also know how to graph this. What we're about to lead into is how to graph the inverses. But before we graph inverses, go ahead and pause the video, evaluate all of these. Next, we're going to look at graphing logarithmic functions. We've got a slide here talking about the parent functions. Turns out that the log functions are inverses of the exponential functions, meaning if we draw that line at y equals x, the graph of b to the x and the graph of log base b to the x are reflections of each other. That's if b is bigger than 1. If b is less than 1, we've got exponential decay, and the log graph is still an inverse of that graph. We're going to learn how to graph these from scratch right now. Neither of these functions have shifts. A shift would look more like this. We'd have like a minus 3 plus 7. That's not happening. So what's left is really just called the parent function. So we write down the parent function. First step, just like we've been doing for quite a few graphs so far. We then have to decide what numbers are easy to plug in. And to figure that out, we're going to do another side quest. What I'm about to talk about is true for every parent function of logarithms. The easiest number to plug into this is 1. Let's talk about why. This is going to equal something. We don't know what yet. Let's figure out why this is what I call easy. 3 to the something equals 1. And we should all know 3 to what power equals 1? Anything to the 0 power equals 1. So y is 0. So that's going to be one easy number to plug into our table. Always plug in 1. Your output will be 0. Now we have to figure out one more easy number to plug in for x. just chose 1. We can't plug in 0. Let's talk about why we can't plug in 0. If we try to plug in 0, we have to say 3 to what power equals 0. And that's never true. 3 to no power is 0. We can't do it. We can, however, plug in 3. I chose 3 because that's my base. If my base was 7, I would have chosen 7. If my base was 12, I'd choose 12. I like this one because 3 to the y equals 3. 3 to what power equals 3? 1. So if I plug in 3 for x, I get 1 for y. So let's extend this side quest a little bit more. Say I had a new problem that looked like log base 7.3 of x. Looks way more complicated. But our table is still going to be nice. First number I'm going to plug in is 1 because 1 is always easy. Log base something of 1 is always 0. The other one I'm going to plug in, not 3. I'm going to choose whatever my base is, 7.3. 7.3 to what power equals 7.3? 1. And by the way, we talked about the number we could not plug in before. It was 0. Turns out that our asymptote is also at 0. So let's rewind back to the problem. We're going to have an asymptote at 0, not y equals 0, but x equals 0. It's going to be straight up and down asymptote this time. As we just talked about, our easiest numbers to plug in would be 1 and 3, because our base is 3. Plug in 1, we get 0. Plug in 3, we get 1. No shift, so we're ready to graph. As always, I will start with my asymptote first. It's a vertical asymptote at x equals 0. Plug in my points, 1, 0, and 3, 1. I'm only looking at 2 points, but those 2 points are enough to tell me which side gets steep and which side stays kind of flat. The directions do not say find the domain and range, but you can believe I want you to find domain and range. Just like everything else on these are kind of flipped backwards from our exponential. This time we don't say domain is all real numbers. We say domain is all the numbers bigger than 0. Whereas the range just goes down forever and slowly up forever. So our range is all real numbers. Notice that kind of flips from our exponential graphs, which makes sense because we switched to the x and the y. These are inverses. We're going to look at part B, put it on a separate page. Once again, we make our table. There's no shift. We'll worry about shift in the next example. We plug in the easiest numbers we can think of. The easiest number is still 1. We'll always get 0. And because our base is 1/2, we'll plug in 1/2, which is really 0.5. And our asymptote at x equals 0. No shift. Always be mindful of the shift, though. It's probably a safe bet to assume that you'll have a shift on your quiz or test. So we'll see that later. Plug in our first point, 1, 0. Plug in our second point at 1/2, 1/2. And we can see that it looks like we're going to get steep going up this time and flat down here. The 2 dots that you plot kind of determine where you're going to get steep and so on. Domain, once again, bigger than 0. Range, all real numbers. In what I believe is our last example, we have one more graph, except this time we have to apply the shift. So we start with the parent function, which is the same as the original function, but taking away the shift. shift we'll use momentarily. Making two XY charts, that's not new. Easiest number to plug into this parent is 1. Remember, you can't plug in 0. We have an asymptote at 0. You get 0 for an answer, though. The other one is to plug in our base, 2. And we get 1 for an answer. Our asymptote is at x equals 0. Now we need to apply the shift. The plus 3 up here tells us we want minus 3 plus 1. Same shift rules that we're used to. At this point, we should subtract 3 from every x value. So 1 minus 3 is negative 2. 2 minus 3 is negative 1. Add 1 to each y value, 0 plus 1 and 1 plus 1. Be careful on your asymptote. We're used to shifting the y value, so you might think put equals 1, but this is an x asymptote, so we need to use the x shift. Now we've got everything we need to make a successful graph. Put in our asymptote at negative 3, x equals negative 3. Plot our points, negative 2, 1, and negative 1, 2. We can see that we're going to get steep going down this way, flat going up. Go ahead and pause the video and try to figure out the domain and range on your own. If you said domain x is bigger than negative 3, good job. Range all real numbers, good job. And that's everything. At this point, go ahead and pause the video and graph all 3 of these, including domain and range. Have a wonderful day.